So welcome to today's class. Today I want to take you through the power system, the power generation, that is for higher national diploma. For the topic that we're supposed to start today is the high frequency transients. So welcome to our class. So today we are supposed to start a new topic. I just want to believe that you are able to see the course outline that you are supposed to cover. And therefore today I just wanted us to do this topic called the high frequency transients. The high frequency transients. Also, we can call it the traveling waves. The traveling waves. What does it entail? Most probably, we just want to check about the voltage. That is not the voltage that is supposed to be used. Maybe some of the times you find that we have some voltage surges, and voltage surges is because of maybe something like the lightning, because we said that the voltage surge is just an abnormal voltage rise and the power rises that can be whenever we just want to, maybe to transmit our power. Now you find that in case of the lightning, something that can occur, say like a lightning, then you shall find that the voltage will behave abnormally, and therefore that will cause to the high frequency transients, or maybe you will find that there is some of the waves that will be formed, and the waves might not be good to especially in whenever we are transmitting our power or maybe our voltage. And therefore today it is very important to check about the voltage surges. Number one, because yes, the lightning will occur, but what shall we do? What shall we do so that now we prevent our equipments that are connected along the entire line? Number one, we know that maybe in our previous topics or maybe in our previous levels, we were able to check on how we can protect the line transmission by using of the power surges, protectors, or maybe the surge diverters. And also we were able to see how we can protect the transformer. You remember about the only gap arresters and so forth. But now, today I just want us to concentrate with the voltage surges, or maybe the high frequency transients, or maybe the traveling waves. And therefore, we can say that a voltage surge is just initiated by a sudden change in voltage in a power, maybe in a point in a system. Or else, we are just saying this, for us to define the voltage surge, there is some of the theory that we are supposed to understand. One of the theory that you are supposed to understand is that a voltage surge is just initiated by a sudden change in voltage in a point in a system. You find that maybe your system was expecting say like 11 kV, but because of the power surges or maybe the voltage surges, you find that your voltage has risen to abnormality, whereby now the voltage that you are receiving is more than the expected, and maybe the voltage cannot be able to hold maybe the equipment like the transformer cannot be able to handle the high voltage, and therefore you find that your equipment will be damaged. So since our transmission system is equivalent to a large number of shunt capacitance interconnected in series with the inductance and resistance, there is a time delay before the change reaches the other part of the system. Or maybe you understand from the overhead transmission lines, we were able to see that in transmission, first we checked about the classifications of the lines, or maybe the classifications of transmission line. Therefore, we said that we have three classifications of transmission line. One being, we said one, we have the short transmission line. Then number two, we said that we have the medium transmission line, whereby we said for the short transmission line, this is now the voltage that will go up to around 20 kV. And also for the distance, we said that this distance will be up to 50 kilometers. That is for the short transmission line. Now, again, number two, we said we shall be having the medium transmission line, whereby under medium transmission line, we say that we shall be having the voltage, maybe the voltage that is above 20 kilovolts up to around, we said around 132 kV. Then for the distance, we said the distance is from 50 to 150. That is another thing that we measured under the classifications of the lines. At the same time, that is for the medium, we saw that some of the methods that we can use to calculate our problems that we have. Number one, we said we shall use the end condenser method, whereby we said in this one the capacitance effects will not be ignored. Number two, we said that we have the the nominal T method, whereby we said now in our impedance, that is Z, is supposed to be divided by 2, because we understand that we usually have the AC circuits. That is now you find that the resistance and the inductance are connected in series, right? So we say that the impedance, that is our Z, shall be divided by 2. And then the capacitance will be trying to act in between to the line. That is what we said. And therefore, for our today, we understand that since our transmission system is equivalent to a large number of shunt capacitance interconnected, the shunt capacitance, this is what we want. That is now the shunt capacitance that is interconnected in series. Now that means we have maybe a resistor, we have an inductor, at the same time we might have a capacitor, and that capacitor, that's why we are saying that the series with inductance and resistance, and therefore if a time delay before the change reaches the other part of the system. Now the delay, now because of this series connection of maybe the inductance, the resistance, and the capacitors, it will delay the change in that voltage before it reaches to a certain point of the system. And therefore, this delay is due to the time required for the electrostatic and electromagnetic field to take place. And therefore, the velocity at which change, or maybe the surge, because we have said the surge is just an abnormality, or maybe an abnormal change in the voltage or maybe the power. That is what we call the surge. So that's why we are saying now that because of our series connections, it will delay that effect. So that now that effect will not reach to the system or maybe to the equipment as it was supposed to be reached before. And therefore, we are saying that the velocity at which change or maybe the surge travel upon the medium on which the surge is traveling. Now we have a typical voltage surge waveform. We have said, you assume this is where we have our 50%. Then we will, of course, this is the side of the voltage. And again, we have the time in microseconds. So because the surges usually happen in a very short time, so that means we will not be able, or maybe the time that will be used, it will be very less. That's why we are using the micro. Remember, micro is supposed to be, we said that micro is supposed to be 10 raised to power, because it's micro minus 6. So it's supposed to be 10 raised to power minus 6. That is micro. We shall be using that one. And therefore, the voltage, there is this race of this curve that is now up to a certain point, the highest point. Then after that, it will start decreasing up to a certain point at, say, like 50%. So that is what we call the typical voltage surge waveform. We can try to explain a bit about our curve. We are saying that the waveform shown in a graph of maybe a build-up of a voltage with respect to time, as I have said before. Now the waveform is 1/50 voltage surge. That is a surge in which, as the peak is reached in 1 microsecond, and the tail, you can see where we have the wave tail, and the tails falls before in a half the peak in 50 microseconds. Now we can say that there is something I want to say here before that. So the steepness from the graph now, the steepness, we are saying that the steepness of the wavefront, is important as it indicates the rate of rise in voltage. That is any point in a system. That means now the breakdown voltage of the insulation varies with the rate of the rise of the voltage. And therefore, we want to check what is the current surge. That was for the voltage surge. So the current change, which is this one, we can say that it consists of the charging of the discharge, or maybe it can consist of charging or discharging capacitance current that is caused by a change in voltage across the shunt capacitance. And therefore, a voltage surge is always accompanied by the current surge, but which travel in the same velocity. You understand that V is supposed to be equal to the current multiplied by the resistance. And therefore, if there is a voltage surge, it means there will be an effect in the current. There will be an effect of in the current. Now I want us to check on the causes of the high voltage surges. Causes of the high voltage surges. What causes that voltage surge? Number one, we can say we have the direct lightning stroke on an overhead conductor. Direct lightning stroke on the overhead conductor. That is now when we have the lightning. You understand that lightning is accompanied by the more electrons which are charged. Now those electrons make the voltage to rise up to a millions of the voltage of the kilovolts, and that one it will mean that our transformer will not be able to handle the voltage that is being transmitted. Now, this may initiate a voltage surge. This may initiate a voltage surge having an amplitude of order 10 millions of the volts. Or else we are trying to say that now because of this one, you find that the voltage will rise to abnormality. Say for example, our transformer might be expecting like that 3 kV. If our transformer is expecting that 3 kV or maybe 11 kV, and maybe you give it millions of volts, then it means that equipment, that is now the transformer, will be damaged. So it is more sphere surge, although rare. This one can happen, but not as much. Are we together? So the thing that we usually do is just to make sure we have protected our equipment as well. Number one, that was number one, and therefore for the number two, we can have just a little bit. I try to adjust my screen. Yeah, sure. So it's supposed to be. Let's see that. Just want to make sure that you can be able to see it physically. So there we go. Now we are saying that number two, that was number one. Number two, we shall have cloud to cloud, that is cloud to cloud, or maybe cloud to earth discharge in the vicinity of the overhead conductor. That means you understand that whenever we are learning about the protection, that is in building that I think it was a diploma in the second year, we were able to find that there is difference, whereby maybe you assume this is your line, this is your line, this is your cloud, this and this one is again another cloud. So we can say, that's why we are saying we can have a cloud to cloud colliding. Maybe you find one is positively charged, the next one, the other one is negatively charged. So the collision might be between cloud, this cloud 1 to cloud 2. Or maybe, again, you know, it can also be a cloud to the earth discharge. It means now, instead of the cloud to cloud, now this cloud has discharged some of the electrons to the ground. That's why we are saying cloud to earth discharge in the vicinity of the overhead conductors. Therefore, a positively charged cloud electrostatic induces a corresponding negative charge on the overhead line, and when such cloud discharges to the earth or maybe another cloud, then it means the negative charge on the line is isolated and resulting in a high negative voltage surge. So number 3, that was number 2. Number 3, we can have the switching on an open circuit line. Like for example, if there is someone who is working under Kenya Power, you find that whenever you are disconnecting or maybe connecting the voltage, maybe you had cut off the voltage, maybe supply on the one side. When you come to place your fuse, that is now the fuse mode, you shall observe that there will be some what do we call it? We call it the sparks. There will be some sparks that will be produced because of that switching on an open circuit line. And therefore, that is just a simple diagram whereby we can have inductor 1, inductor 2, inductor 3, then in between we have a capacitor 1, capacitor 2, a capacitor 3. Then of course, because we assume that line is already having some of the load. So that load is what we are saying the L1, then L2 for inductor 1, inductor 2, inductor 3. Then we have the capacitor, which is now between the line and the neutral. We have the maybe the capacitor 1, capacitor 2, and capacitor 3 that is connected to the to our line. Now, when you start switching this one, because of that load, there will be some of the sparks that will be produced. Those sparks makes the voltage to be abnormal. Maybe for the person who is receiving the voltage might find your voltage, maybe the voltage being received is much higher than the expected. So maybe in explanation we can say that when the switch is closed, our switch is here, E, does not instantaneously appear at the receiving end. And therefore, E, which is our switch, now is first opened by back EMF induced in L1, that's now for the inductance, this one, by the flow of the current I to the charge C1. That is now for the capacitor. And therefore, the voltage that will be developed across C1 will cause the current to flow through L2 to charge the capacitor 2 and so on. You find that now this capacitor 1 will be able to charge the capacitor 2, which will also be able to charge the capacitor 3. Now, the time delay before E, there is that time delay before E. Remember, E is our switch. So the time delay before our switch, that is E, it appears at the receiving end. Is due to the continuous interchange of the electrostatic and electromagnetic energies along the line. Another number 4, we can say that there is short circuiting a transmission line. Maybe you have line, 3 lines, which is L1, L2, L3. Of course, you know it's RYB, red, yellow, and blue. So if we are saying that the short circuiting transmission line, you find that maybe there is a short circuit between L1 and L2, and therefore that shows that at the fault the voltage is suddenly reduced. You find that at the fault the voltage is suddenly reduced to 0, causing a surge redistribution of the electrostatic and electromagnetic energies. Another point, which is number 5, we can say that an arcing, we learned arcing. What is arcing? By the way, in protection we learned that. So an arcing ground fault. Now, this is an earth fault on one phase of the insulated neutral system, and therefore the voltage phase will have its potential lowered to such an extent that the earth will be extinguished, and therefore at this instant, then it means now or maybe it means that the potential of the earth phase suddenly will rest, or maybe rest, that the voltage surge are initiated. Number 6, another cause, which is number 6, we can have the interaction of the load, or maybe the fault current by the fault current by the switching. That means now this causes a sudden redistribution of electromagnetic and the electrostatic energy, whereby now the severity of the resulting surge depends on the rate at which the arc is extinguished in the circuit breaker, and therefore I want us to check on the surge velocity, this one. You can just check this that wave, whereby maybe we have the wavefront, we have the wave tail, and we have the voltage side, and of course we say this is our time in microseconds. That is our time in microseconds. So we are saying that in theory the voltage surge will be assumed to have the waveform shown instead of typical waveform shown previously. So that means the severe or maybe a very stiff waveform, wavefront of an actual surge is assumed to be vertical, and the long tail of the actual surge will be assured to be infinitely long. And therefore we can say that also the system is assumed to be loss free. That is now the resistance of the conductor is 0. The resistance of the conductor, remember that V is equal, we say that V is equal to I multiplied by R. So we shall assume that our R is not 0 but almost 0. Because if we put 0, it means the voltage will be 0. But if we can put this R to be 1, then it means now the voltage will not be affected by it, or maybe it will be affected by reducing the value of the R. And that of the insulator is infinite. We are saying that of the insulator is infinite, and therefore this assumption simplifies this theory. So the actual surge is less severe than the theoretical one because the resistance losses in the actual system reduces both the magnitude and the wavefront gradient of the surge. That means now the initiation of the voltage surge will be represented by closing the switch. You assume now this is our switch. You remember, whereby this is our load. We say it's our load. Yeah, that is our load. Now we have to switch this side there. And of course, this is the side of the sending. You remember that we have the sending end side and the receiving end side. So our load acts as the receiving end side. So that's why we are saying that our load will act as the receiving end side, and then this side will act as the sending end side. Now we want also at the same time we have another receiving end side here. Now that receiving end side also is just want to be supplied by the voltage or maybe the power at the same side, same thing with the other side, and therefore we shall be required to switch, just because we explained about the switch, so we shall be required to switch the voltage, our switch, and therefore we can say that assuming the lining is uniform, the vertical waveform, that is E.
Kindly, I have a question.
Yes, just feel free, kindly.
Can I ask?
Yes.
I think I didn't get the relationship between the surge velocity and the switch we are talking about right now.
The surge velocities. Okay, that is from the causes of surges. You understand the causes of the surges? I think you joined our class on time. because that is what we talked about the what are some of the causes of the surges, and therefore switching was one of the causes, right? Whereby we say now that when we want just to connect our switch, then it means there is some of the spikes that can be able to see. That one will make the voltage, or maybe the power being supplied, to be much higher than what is required. So switching was one of the causes of surges. And remember you remember that this topic that we are talking about is about the surges, right? So I don't know whether you have understood me.
Can we go back to upper surge velocity? Let's start there.
Like for example, okay, surge velocity is supposed to be here. Sorry to see. I don't want this one. This is what you're talking about, the surge velocity. Yes. What is the question?
Come up again. Let's start hapo for surge velocity. Can you start explaining that so that we get the relationship between that and switching, of which I was in class. Na process moja ilikuwa switching on a lot of open circuit and blind. I get that. But I need a clarification from surge velocity.
The surge velocity. This is just the wave that you are seeing here, whereby it's very labeled well that this is a wave front. Now you understand the other one, we add like a rise, then a tail. You remember? Then that tail was having at a certain, are we together? So what we have just taken is just what we have here. Are we together? So that is, this side is the wave front. That is the wave front. Then if, which is here, of course, I'm just trying to transfer what we said before. Then we have this one. No, let me just, because now you have understood, I want to remove that one. Because you know, at least now you understand where is this coming from, right? To the person I'm explaining to. Yes? Are you able to see that?
Yeah.
Yeah, so this is just from the previous, what we are talking about. So we have just concentrated. We have just concentrated with this part only. Now that is where we are getting the surge, because now we want to talk about the surge voltage, about the surge velocity. So this one, we have said this wave front is here. Then we have the wave tail. If you go back to what we were saying previously, you shall see the wave tail somewhere. Wave tail. And also, of course, we said this side. This side is the voltage. Then here, we said this will be time. But now that, because that thing is happening with a very short time, we said it will be in microseconds and not seconds. So did I explain to you as you were expecting?
Yeah. For the diagram, I'm okay. Now can we go to the theory part where in theory the voltage that one?
Okay, actually that is what I have said. Only that now, let us go just there. We are saying that in the theory, the voltage such will be assumed to have the wave front, or maybe the waveform as shown instead of a typical waveform shown previously. The previous one ni yenye ilikuwa na we add someone like that one. So